So we are live now, but there's still, do you see any attendee?
The attendee, they will arrive.
Okay,
we will just wait a couple of minutes so people can connect and join us.
Yeah.
And then we will start.
Right. This must be evening for you guys, like almost 4:30, 3:30. What's the time there?
Yeah, not yet the evening, but yes, it's the middle of the afternoon. It's 3:30.
Okay.
Okay, so I will start, make the quick introduction, as I said, very quickly. So hello again, everybody. Thank you for being here with us for the third and last session of today conference. So for those who were there the past days, I'm here again with Amit Kumar. So I'm very pleased to have you again with us, Amit. And Amit is part of the PSIM team, the developer team. So he's a technical application engineer with the team, and he participates in development and specifically also specialized into resonant LLC and resonant CLLC design tools, like the Power Design Suite, for example, for those of you that know this design suite. But not just this, of course, also power converters that you can find in PSIM. He's also part of the technical support team, so you may chat with him already if you contact them, the support of PSIM before. But that's it. So thank you, Amit, again. I will give you the end now so we can jump in directly at the techniques.
Okay, so can I start sharing now?
You can start sharing now, yeah.
Okay, perfect. But actually, you have to make me only this you have disabled.
Yes, it's okay now. Okay. Normally, it's okay.
Yeah, it's okay now. I can see.
Okay, perfect.
So you can see my slides now, right?
Yes, perfect.
Okay, perfect. So I will. So just let me know when I switch from slides to the simulation, whether it switch back to the switch to simulation or not.
Yeah, no problem.
Yeah. Okay, so I will start now. So hi everyone. My name is Amit. I am a application engineer with PSIM, and we are the maker of software PSIM. Today's presentation is on design of high performance motor drives in the software PSIM. Mostly I will be doing a simulation. I will just go through the few of the slides, and mostly I will be talking about our motor design tools through simulation, live demo for everything, and then we will have a Q&A. This slide. So first slide is actually about our comprehensive, or you all know how generous our motor model library is. It's full of different kinds of motor with different level of complexity, from linear magnetics to non-linear magnetics to spatial harmonics to high frequency input impedance, different phase, 3-phase, 4-phase, 6-phase you can have. So for PMSM, you can see, like I said, linear here means that your LDLQ is not a function of your current, IDIQ current, and non-linear means your LDLQ, basically is a function of ID and IQ current. And similarly for induction machine too, we have a linear, non-linear LM there, magnetizing inductance there. And then we have high frequency support for IM2. And then if you want to do some fault tolerant analysis or those for phases, you can do that too for IM. And this is something linked to FE2 like JMAG. This is something right up the alley for this conference. So we provide a link to different third-party software, and one of them is JMAG. And with JMAG, we can easily import. I'm going to show you all these things, how we can easily import RT files, realistic machine models from there, and that is going to help, and we'll simulate it, and that is going to help us finding the losses and the torque control or speed control we are doing in a realistic motor model. And as you know, with this finite element analysis tool of JMAG, we can have as much realism, realistic approach in modeling the motor there. So it's a very handy tool. And I'll talk in detail a bit later. Then we also have switch reluctance, so 3-phase, 4-phase, 5-phase with linear, non-linear flux and torque relationship and synchronous machine we have with external excitation, and all these motors we have. You can have a 4-quadrant operation, either motoring mode or generating mode. All are possible. So motor control design switch. So this is something, if you are a PSIM user, or this is well acknowledged in motor market or motor drive, that motor control design suite is an integral part for designing motor, actually the overall control loop system in PSIM. So this is something I will be talking about, our different templates we have, some new templates we have from our last or current release. So in this template, we will be seeing all these points live in action too. Like I said, I mean, motor control, so we will be doing complete closed loop. So we will be able to generate in digital domain or G domain or Z domain, PI controllers, PI gains for both your torque or outer torque or speed loop, or an inner current loop, that is for ID and IQ too. We will be able to get digital PI gains. And all these controllers are based on you defined, based on your bandwidth, crossover frequency you defined, or sampling frequency you choose for your digital system. There, these controllers are actually user defined in that way. You are basically designing your own controller there. And this is something of important to all of us, generating efficiency map of overall drive system, including the inverter losses too. So we will be doing this with JMAG. We will be getting realistic model from JMAG, and we will be calculating switching and conduction losses for the inverter in PSIM using our thermal module, and we will be summing up the overall losses, and we will see how the loss is behaving with what's the profile with the speed there. And then the control algorithm working there, not only the outer and inner loop I talked about. Actually, the reference current we are generating ID and IQ there is actually optimized ID and IQ based on your speed, wherever your speed is. So if your speed is less than base speed, you will be we'll be doing optimization based on max torque per amp there. MTPV control. Field weakening after base speed, we have some back EMF, and we will be doing field weakening to weaken the stator flux there with some by negative ID, making the ID more negative. It's a very fundamental of FOC control, field oriented control. All and MTPV is something we have also added, that is to control the motor in higher speed region. So MTPV, maximum torque per volt. So all this control is based on your constant optimization problem to solve, to get the optimal ID and IQ. Based on those voltage limit equation or current limit equations and all those things. And all the template I will talk to you is completely editable. So this is basically the one template we have here. And I will just go after this to simulation to show you this template, all these templates. So this is kind of a punchline we are going to have in this presentation. I mean, this is what we are going to aiming for. In the right bottom, you can see the efficiency map here, right? And here you see that your inverter is there, is feeding to your a realistic motor model. So we got this motor model from JMAG RT, and we got the RT model. So whatever the control scheme we wanted here, we did to torque control or speed control for this template. And we calculated the overall drive efficiency, right? And we got that for different torque. Basically, what we did, we run a script here for different torque commands and the speed, different reference speed. We got run multiple simulations, and we got this torque versus the speed curve for whole system. So we have added the losses happening here in inverter, that is switching and conduction losses. So we have thermal module for that. We will show also that we can see that which switch, which IGBT or silicon carbide MOSFET we are using here, and all those things. So, and also we have using, let's say, a space vector PWM here for this case, let's say. You can have a different DPWM, DPWM 1, 2, mean max, DPWM mean max, different schemes, whatever going on. It's totally editable. This also, you can have a multi-level inverter. Let's say if you want to have some multi-level inverter there, and you can easily change the control scheme here, right? So what I will do, I will just go in my simulation now to show you all these things in live action. So first of all, so you can see my welcome page. This is the for PSIM, right? So here we have all the design suite we can see here. So we are talking today about motor control design suite. What we can do is that open some. So first of all, these templates you see is based on uh, linear, nonlinear magnetic. So we can see that it's a linear IPM. Your LDLQ is not function of IDIQ. Nonlinear means the function of ID and IQ current here. This particular template is actually specially dedicated for your JMAG, right? So I will talk about this template. I will just want to quickly go through all the templates. So use all the tops are speed control. It's not mentioned there. That means it's speed control. And the bottom, when you see these two are torque control, then we also support some sensorless based on the target hardware from TI, sensorless drive 2. And we also have also here we have a template for induction motor drive, and we have lots of different examples with different complexity for IM drive 2 in our motor module. So I can start with this fundamental template here, which is linear IPM, right? So it is easy to understand from the beginning, and then we will go towards some of the other uh, template. So this I already run it. You can see the result here. So what's happening here? This is actually the result for this particular template. So we have able to track the reference ID you wanted, as you see, and actually it was designed for your 800 reference speed you wanted, and we have finally in steady state we have got there. So what this flag is showing here is that in the beginning we have 0. That means there is no field weakening there. So in the beginning we have a MTPA working here. So this is the base speed, and below base speed is MTP. Then we have a field weakening coming up here. And you can see the field weakening, we have more negative ID current going here. The reference change, and that's how it's tracking there. And then we have a field weakening plus MTPV in higher speed region. And finally, when we got the steady state, we get back to the field weakening here. And the torque you can see is torque of your electromagnetic torque is there. It's a speed control. So we wanted to do speed control here. And I can talk a little bit about these loops here. So speed loop, you can easily see the PI I was talking about. And for your current loop too, we have two PI loops and all in digital domain actually. And all these gains, you can actually see it here. Right, so you can see these actually on the left. I can say that you need to first of all define the parameter you wanted. So you define your for let's say this inverter, this much your DC bus voltage, then inverter your characteristics, your switching frequency, your max current for this inverter, then your moment of inertia and load of the torque, and then your stator resistance, pole, LQ, back EMF constant, all you define here. So this is easily editable. You can change it anything. You can actually, I can show you. You can, if you click here. So even without running it, you can see how your torque versus speed, your constant torque, and then your constant power. Basically, your power profile is going to look as a function of speed. And if so this is a very important, very easy to do. You can do it here. And this was the thing I was talking about, that this is something what is up to you. You need to select your sampling frequency for your speed loop, your torque loop if you're doing a torque control, and your sampling frequency for your inner loop. Also, you need to select based on whatever discretization you want there. And then you are selecting your bandwidth there for your basically your crossover frequency for your current loop and your speed loop. Speed loop. So speed loop, of course, I mean, based on we are around 1K is our bandwidth for current loop, and 100 hertz is a bandwidth for our speed loop there. And based on that, the bandwidth we selected there and the sampling, we calculated the gains and as well as our phase margin. for stability. For let's say for current loop, we have this 57 degree phase margin, and for for current loop, and for speed loop we have around 78 degree phase margin. So all these are internally calculated. If you change anything and update it here, it will calculate a new set of control gains and everything. And so this is about this template, and this template here is actually to show you what you call, I will actually run it here. So this is from JMAG RT. This in this particular template, it's obvious that we have a LD-LQ coming up here as a function of, so it's a non-linear IPM, right? And we have a, so in this, what we do is that import RT model file. So let's say actually we have this RT model file. It's designed for 10K kilowatt PMSM. And I have, let's say somewhere, let's say this file here, new RTT file for 100K. So I can replace this and update the whatever specs is changed for that, or based on we got from the JMAG, we can there. And we can, so in this case, we have a accuracy type LD-LQ. We can have a flux integral or spatial. One example I will show where we have a spatial accuracy too in our, from our application note. So this is complete. So for this one, like I said that we have included the realistic motor model. So that's why apart from all the same principle, like the other template, the control loop, the current loop, everything is there. And this optimization box for generating an optimal ID, we also able to generate the losses, your copper loss, your eddy current loss, your iron loss, you can see here. And the LD-LQ, you like was saying, it's a function of ID and IQ. It's the way it's changed, your LD-LQ, it's changing right there based on the tracking. IDI, you can see it's tracking the way it's changing there. And you can see your current, three-phase current is accordingly, it's whatever it's there in three-phase, right? And so all these things I already discussed, that you can easily change this. You can, if you want to use speed of the simulation, you can have an average model of the inverter. You can easily change it to average model, or and other this thermal I will talk if I have time, based on the time I have. And you are easy to edit anything you want to do. You can easily edit these things. And one example I have here, I can show you from our what you called application note file I have. Let me see. So this is this particular example we have. This is I will show you where you can find this application note file, and also I mean it's also available in our website. You can read about it. There's a very detailed. So this particular template is, we are actually, you can see all these parameters are changed here now, right? For earlier one we have some 240 or 84 amp. Here now it's 100 kilowatt actually PMSM design, and we are getting that same the lookup table basically from your or the realistic machine model from your JMAG. And we are actually doing efficiency calculation for overall drive system here, because here we have included the realistic device model, basically a thermal model for this IGBT. And you can click here and actually we can check here. I mean all the parameters added for IGBT or E on E of characteristics, or all any other, I mean the basic characteristic of a switch there. If I have a time I can show you. So the main thing is that once you do all these things, if I go back to my simulation, I will just go and finish this, and I will show the result I have for that particular. So that's what we did here. Precisely what we got the result here. We got the motor model from JMAG, and we put it in our design suite, and we simulated everything, and that's the result we got. And this is something we did case study. When we changed the, like I was saying, with space vector modulation, we have different loss. Like we also changed a different PWM scheme, and we got actually if we did deeper PWM1, we got 20% improvement there. And you can see for both cases the loss comparison is there. And so all these things is very easy to do in our design suite. And this is what I was talking about, that once you have a both in a thermal model of your of the inverter and the realistic machine model, you can easily get full drive efficiency. In that, you can have an inverter, separate inverter efficiency, as well as motor, and you can also combine it. And so basically, this is what important for us to see the torque speed profile in our for in different speed region. Maybe for inverter losses, you have a different speed region, better efficiency in different speed region. That's what, or for motor losses, we can have a different speed region. That's what you need to look into. And so this was the scripting written in order to get some of these efficiency map. And scripting is also important to compare, like we compare different, you can have a different devices to here. So you can have a change back this device. You can run a different script, multiple simulation with different device model. Somebody can compare IGBT and the silicon carbide MOSFET losses, and or any other different from different manufacturer. You can do that. And so this is it. This is what I wanted to show all of you. And in conclusion, I show you the speed torque capability, which is very easy to see the maximum capability of motor without even running it. MTPV control was new, we have added for higher speed region. And all these new templates are available, which link our design suite with the JMAG RT. Very easy to import the file and run the realistic machine model there to get your efficiency map and all those things. New control blocks are there, new 6 control. I can actually show you this control where you can find this thing. Let me just finish the last line. The last line is what the sum of everything. You want to have generate the efficiency map, the whole drive system end of the day. After putting all the realistic thing there, after doing all those finite element analysis and incorporating a real motor model in JMAG and importing back to PSIM, and then simulating and getting our efficiency map there. So I can take question and question answer if there. And these are our link for our resources and contact you can do. Here the control blocks are here. I wanted to show all of you. Here, if we have for our motor drive, you can see all the list of motor model I was talking about. For induction motor, of course, we have like squirrel cage or wound rotor based on whatever you use in your application. Different PSIM, SRM with different phase and all. And if you go to control here, you will be able to see our basically here all the control blocks, like for your speed control torque and all those is available here. So so these are easy to find too. If you want to use, if you don't, you can also search from here. You can directly write the name here too. And oh yeah, so this is it. This is what I wanted to present to all of you. And if any one of you have questions, I can take, and we will go from there.
Thank you, Amit, for this nice presentation. So I see first question. We have still a few minutes, and we can go a little bit over time because it's the last session for today. So feel free to ask any question in the chat or in Q&A section directly.
Yeah.
So first question.
I see one question, that how to get efficiency map for inverter only. Okay, so I just saw to you that for that inverter, let me just go back. So for inverter, what we have, if you look at here, so this one, which one? Over here, right? So inverter, you need to use thermal module. So thermal module is something utilities. We have here device database editor. It will take some seconds to open up. So this is what we did. So in device editor, what we have for different MOSFET, IGBT, or diodes, or any switching devices for different, based on the manufacturer, we put. So let's say we want to use IGBT from ST, let's say, or something. Actually, we do not have from ST a MOSFET, any MOSFET. So we can come here and we can find any from where is Infineon? Infineon is here. So we can see different MOSFETs we have. If you want to use IGBT from Infineon, look at the list here. So we have all this IGBT. I mean, it depends also whether manufacturer make for that rating or not. So let's say for this 100 kilowatt rating or voltage and current rating, this 500 and this current, we need to select the parts here and we can easily come and bring it here. For that, we need to we can actually we can have a, like, if you go to your MOSFET, so if you can select from database, so you can bring it here and easily add here and calculate the switching conduction losses. So this is calculated from inside the PSIM to answer the question of the gentleman. So this is easily, you can also select whatever MOSFET you want. Let's say you directly want to use 6-pack. We need to select the part which supports 6-pack. And also we need to take care of rating and all those things. And if you want to go from scratch, you can add your own IGBT, MOSFET or diode, whatever you want. And same way, you can add it here. It's very easy to add. Like you said, you can have, we support different switching model. We have a level 2, ideal, thermal, and then SPICE switch models too. So that you can do.
Thank you, Amit, for your answer. Do you see there is another question in the Q&A section?
So I see previously we faced problem with FSM. Is it added now? Can we import it? Would like to answer this question. Matt, you want to answer him?
No. I'm just clicking to.
Oh, I see. Okay. What he meant by FSM?
No, Jan, you can precise your question if you want in the chat or in the Q&A.
Yeah, let me check. I can't see his question. FSM.
He said flux switching machine.
Flux switching machine. Flux switching problem with flux switching machine. I mean, you can see all the motor we have, motor models here. Is it flux? Is it? I mean, I'm not. I mean, totally from motor control field. I have done courses back in that school, but motor models, all you can see here. And I can, if you can explain what kind of machine you are saying by flux switching machine. Oh, synchronous machine is a typo of, oh, you did, okay. So you wanted to say synchronous machine, okay. Yeah. So you have a option here, synchronous machine with load, with a function of I, and you have here, you can easily add it here. So if you want to click here, this is the synchronous machine right here. You can, if you don't want to use this suite, you can come here, file, open it new, add, start from a scratch. So whatever you want, you can start adding. You can add inverter here too. This design suite is something we have here to ramp up your speed so that you're concerned about the machine, your control loop and everything is sorted out in minutes, right? These things, if you start from scratch, take days, months, right? If we, and you can see how impressive it is that to control and get up to the desired the point we want, right? For reference we want, right? It's something doing optimization here is something is quite unique we have here. This is our own algorithm working here to optimize IDIQ. So something that's why design suite is there, but you can also do it from scratch if you like. There's no problem with that. Any other question we have?
Thank you, Amit. Yes, I have questions on my side from other attendees that
okay.
Directly. So is it possible to edit the schematic and tune it?
Yeah, that's what I'm saying to you, that here, see that let me show you one example of it. So okay, you can see it here. This is made from scratch. This is an induction motor with a cable and high frequency effect. And we have made it from a scratch without using design. So it's totally editable. But to give you just to insight, so look at here. So this parameter file is easily editable, right? And look at this. We have this characteristic here, right? And if I change this to 200 amp now, just to give you a perspective here, and update the file here. Actually, we need to do it here too, right? Update the file here and then generate it. So you can see here that our base speed is now more than 2K. Previously, it was less than. Okay, let me not cut it and show you again, make it 400. So it's easily editable that you can edit it. You will be able to see a new set of curves there. So you can see here, it's now your constant torque region is different than this particular curve here. Anyway, my point here is that you can easily, basically you can edit using your own application. You can have any, practical application here, and then you can go from there. And even this example, we edited it. So we have the design suite made, and we made it for, this was made for, template was meant for 10K. This particular, we made it for 100K PMSM. And for that, we also wrote an application note. Actually, I can show you here. So this is the application note here. This is right from scratch. We made it from using template. We designed efficiency map for this new motor model here. So this is totally new here. So if you look at here, this is it. We got it from the JMAG. This whole, we need to follow practical considerations. We got all these values from JMAG, and we come here and updated it for that particular example, and we run it a new template basically.
Thank you.
Any other questions?
Yes, actually, I have received some other. Okay. Can I have access to the internal calculation of the PI values?
Yeah, you can see the PI values. Yeah, it's right here.
Okay.
For, let's say, for this case, we have your K, your proportional and time constant is there, PI gain and PI time constant. For any template, you see it's there. I believe he wants to know the PI gains, right? How? So if you can look at here, you can see it's a very standard PI control we are doing here. It's in the discrete system, right? The way we are this ID actually is coming reference is a optimal ID and IQ, right? Based on the speed region we are, MTPV or field beacon. So that is something our own algorithm is working there to basically it's a very complex algorithm. If you see, when you have a saturation effect, your LDLQ changing with this current, then it's quite complex to do maths there to get the. But you can easily get these PI values to use it for your hardware, your microcontroller, or whatever.
Okay, but can we have access to the mathematical equations?
I think, as far I know, I think we do not provide. We can provide you some literature where you can read all these things and design your own mathematics. But as far I know, we cannot provide you the precise mathematics we use, but we can provide you some literature, some papers which you can follow. And that's what it is. But yeah, the short answer is that we cannot provide precise mathematics working there.
Okay, thank you. And I have one last question from this person. Thank you very much, Jean-Michel, for your question. Is it possible to create efficiency map picture with PSIM?
Yeah, we did it with PSIM only. So if you look at this particular result, we got it from PSIM only. This efficiency map, we got it, look at here, we got it for inverter only, also for full drive, also for motor. And actually, I didn't run it live. We actually run it for 42 minutes to generate this kind of a thing. And also some other automation there with different PWM schemes. And so for that, actually, we have done a webinar. So if I come here, so here is our resources. You can look at the webinar where my colleague Albert and Mark have gone in detail to go through scripting and all. And you can actually contact Albert or myself. That's my email. That's Albert Dunford. He is, PCM inside out. You must all be, maybe all be knowing him. And we can also support. You can also support. We have a very strong support team. You can also write if you have any question, feedback to there too, or you were stuck anywhere there in the simulation. And you can access all these webinars in this is our page, right? So you come here and you just need to, so if you come to the main page and go to webinar, just click it here. And you can see reach our, it's a very comprehensive library of webinar we have. We do every second week. We try to do one webinar on different topics. So where is the motor? So here all the motor drives are there. Since I have a conference call, my internet seems to be on slow. So anyway, you can see actually all these. We have, in this particular webinar, we have gone with this to generate live those efficiency map, which I am showing here.
Okay, thank you. And I have one last question from Michel. Can PSIM draw this picture by itself? I think you mean this picture.
Yeah, actually, to generate the code, actually, I can show you. I can, let me just see. I can find the code. So what's it from that application note file I have? So what happening was the script, right? So efficiency map script. See, so we have this script here, right? So what we do is that in order to get efficiency map, we need to have this different range of speed commands, right? Like different reference speed. Let's say from 1,000 to 9,000 RPM we varied, and the torque command from 20 to 200, right? And whatever per unit or whatever. So this we can make it more. So this is your array for this thing, and we run it. Currently, if I run it, it will take like half an hour or something to generate this particular efficiency map. So this is right from this from the PSIM only, and actually we cannot do. We got the data. We plotted this in the using the plot diagram in MATLAB. So if I recall, I mean that's what's happening here. But otherwise, all the data I mean data by mean that let's say for any torque command and speed, we got all the data. I mean this is full of data, right? We got through PSIM simulation only, right? And script only. So that precisely what happened in PSIM. So you can actually you run this thing. You have access to this. So if you are a PSIM user, you can find this in application notes. So this is my PSIM folder. I can come here, and the first folder is application note. So this is one or two. If you look at here, so this is for efficiency map. Oh, actually, I have the file. See, I have this file for the M file for MATLAB. So data we imported to the M file of MATLAB just to generate it. Otherwise, everything is in PSIM only. And you can play with all these script and simulation if you like.
Okay, thank you. Thank you very much. I have no more question from Jean-Mich. I don't see any other question, neither in the Q&A or the poll. I think it's all clear. So if you forget that you had a question and you want to ask later, it's still possible. You can reach out to Amit directly into Wova platform. And then he will be able to answer you. I think we will also copy and paste the email address of Amit inside the chat. And like that, you can send any question. I just have a last extension of the Mahesh question. It was the first question. Can you see it, Amit?
Yeah, I see. Yeah, exactly. Yes, just yes. To answer his question, are you saying we get the losses from PSIM and plot it in exactly? Yeah, that's what we did. Yeah, we got all the losses from PSIM multi simulations only. Yeah. Okay, I mean, for both inverter and driver.
Okay, great. Thank you. So thank you very much, Amit, for your time and your presentation. I will just make a little announcement regarding tomorrow's morning. So normally we should have started at 9:50 a.m., but there is a slight change. We will start the conferences. The first conferences will start at 10:10 a.m. So make sure you attend and you'll be there. So it will be a little later than planned, but you should also have received an email from Frédéric Perret about this change. So thank you again, all the attendees, for your presence, your time, your questions, and thank you, Amit, for your
Yeah, thanks
report.
everyone. Yeah, I am here for the coming few days of this conference. And if you have any feedback, any question, any about PowerSIM, PSIM software, you can always reach me or my team. And good luck with all the other talk and presentation.
Amazing. Thank you, Amit. Bye-bye, everybody. Take care.